Hi guys, once again a warm welcome to you. So in this part we have to study current loop as a magnetic dipole and dipole moment. So you must have studied about this thing as when the current flows in the loop, then this induces the field lines, and these magnetic field lines are the closed loops. Hence we have the poles, north pole and the south poles. So for this detailed discussion we are going to study in this part. Hence let us see. Now guys, current loop as a magnetic dipole and the dipole moment. Let's proceed. Now, current loop as a magnetic dipole and the dipole moment. Now let's look at the current loop as a magnetic dipole. Now let's look at this loop. This is a loop which shows that which carries a current in the direction as shown in the figure. This is the direction of the current. Now this is the center. This is the center of the loop. Now this, if we make the diagram, like if we make the axis, this is y-axis, this is x-axis, and this is z-axis. Now according to this, the orientation of the axis, the plane of the loop is in the yz plane, or the plane of the loop is the yz plane. Okay, let's proceed. Now as we know that we must have studied this thing, that current loop induces the magnetic field. So the direction of magnetic field we can find out by the right hand thumb rule by curling the fingers. By curling the fingers in the direction of the circular current, that is, this is the circular current flowing in the loop. So by curling the finger in the direction of the current, this will going to give, or the thumb will point towards the direction of the magnetic field. This you must have studied. Okay, now these what is this and this, what is this symbol and this symbol, what is this symbol, this S, and what is this symbol? Okay, what does this mean? If we look at from the left side, the current will look like as if it is moving in the clockwise direction. That means I'm making the figure. If I look the figure from standing over here, if I stand over here, I look that the current will look like as if it is moving in the clockwise direction. This is exactly the figure. Now that means if I draw something like this, if I draw the symbol S and extend the line something like this, so this will going to point as if this will going to act as the south pole. Therefore, what do we say? If you look at from the left hand side, the direction of the current will look like as if it is moving in the clockwise direction. So therefore this will going to be act as the south pole of the current loop. Now if we look at from this side, so from this side the direction of current will be something like as if it is moving in the anti-clockwise direction, something like this. That means this is moving in the anti-clockwise direction. So this will look like something. If I make N in this and extend the sides of the N, something like this. So you don't have to remember all these things, that what is south and what is north. You simply have to make S or N and extend the sides. So this will going to give you the direction, that what exactly it is, whether it is a south pole or whether it is a north pole. So therefore by this figure, what do we say? That if the current in the loop is moving in the anti-clockwise direction, this induces a pole, that is the north pole. Therefore these are the symbol N, north pole, and the south pole. This is what exactly it is showing. Now this shaded area, this shaded portion is the area of the loop. This denotes the area of the loop. Now if we want to find out the direction of the area, so if again it will comes out to be same. If we curl the finger in the direction of the current, this will comes out to be same as the direction of the magnetic field. Now here we have the tip. Now this tip is when we look at any one side of the loop carrying current, if the current is in the anti-clockwise direction, then that's said to be the loop behaves as the magnetic north pole. So therefore we have already discussed about this thing, that if the current going in the anti-clockwise direction, so it will act as the magnetic north pole. This is what exactly this figure shows. Now, and if the current is in the clockwise direction, then that side of the loop behave as the magnetic south pole. This is exactly the same thing. This we have already discussed it over here. Now these are the same thing. Now this, therefore we call this as the current loop acting as a magnetic dipole. And we know what is a dipole, that you must have studied in the electric dipole. That means two charges plus minus. So we have already discussed that isolated monopoles does not exist. So therefore there must be two monopoles there. That means two monopoles will exist together. So therefore that is called the dipole. One south pole and another is north pole. Okay, let's proceed. The dipole moment of the current loop. Now dipole moment of the current loop is the magnetic moment. This is magnetic moment. This we have seen in the last part. This is the symbol which denotes the dipole moment. This dipole moment is the I into A, that is the current flowing in the loop into the area of the loop. This is what exactly it means. So we have seen that. So what is the direction? What is n cap? N cap will going to give the direction of the magnetic dipole moment, and n cap will be in the direction of the area vector, or else we can find out the direction of this magnetic moment. Simply you have to curl your fingers in the direction of the current. This will going to give you the direction of your magnetic field. This will going to give you the direction of area vector, or this will going to give you the direction of the magnetic dipole moment. And what about the SI unit? The SI unit, it is current into area. So we know that the unit of area is meter square and the unit of current is ampere. So the SI unit is ampere meter square. Now let's proceed further. Now we have to see that current solenoid as a magnetic dipole or a bar magnet. So you must have seen that what is a solenoid. Solenoid is it's some winding of the current loops, right? So this is what we know. So this is what exactly it will going to look like as. So if we look at from this side, this is exactly the same. There are many windings of the current loop. This winding, this winding, this winding, this and this. So there are many windings of the loop, and these are the terminals of the windings. So these are many current loops. So this is what exactly the solenoid. Now if we look at, now this is the same thing. If we look at from this side, so this will look like as if the current is moving in the clockwise direction. So clockwise direction, therefore this side will going to act as the south pole. And if we look at from this side, if observer is over here, the direction of the current will look like as if it is moving in the anti-clockwise direction. So therefore this side of the solenoid will act as the north pole. Therefore the symbols south pole and the north pole, these are the symbols. So this is exactly the same thing. So this solenoid will also act as the magnetic dipole, or it will none other than it is equivalent to a bar magnet. Okay, now let's proceed towards the examples. Okay, when two coils each of radius r and carrying current I are lying concentrically with their planes at right angle to each other, then magnitude of the magnetic moment. Okay, that means first of all it is given that two loops of radius r are lying concentrically with their planes at right angle to each other. How can we make the figure? The figure will look like as if let me draw the figure. This will look like as if the loops are something like this. The loops are something like this, and this is one loop, and if I make the other loop will look like as this. This will be the other loop. Okay, if we make the orientation of the axis according to this, these are my axis. This is y axis, this is x axis, and this is z axis. Now according to this, let me take this as my loop number 1. Now these are concentrically, so therefore the center of the loop will be same. So therefore, and these are, although also their planes are also at right angle to each other. So what do we say, that if this is loop 1 and this is loop 2, so according to these orientation of my axis, so what is the plane of this loop 1? So according to the figure, the plane of this loop 1 is in the xz plane. And if we look at the coil number 2, the orientation of the coil 2 is in the, or the plane of the coil 2 is in the YZ plane. So this is YZ plane. So if we look at the diagram, if we look at this orientation, so XZ and YZ planes are perpendicular to each other. Now let's proceed further. Now the direction, it is given that these are having radius r and these are carrying current I. Now the direction of the current is not given to me, so if I'll take the direction of the current somewhat like this, so it's my so I'm taking the direction of the current by my choice. You can take other direction also, so therefore I'm taking the direction somewhat like this. So if I curl the finger, if I look at this loop 1, if I curl the finger in the direction of current, so it will going to if I curl the finger, so it will look like as if the magnetic movement is coming out in this direction along the y-axis, somewhat like this will be the magnetic movement 1. So but if we look at the coil number 2, if I curl the finger, so the magnetic movement will comes out as if it will comes out in the direction of minus x. Just curl your fingers, it will going to give you the direction of the magnetic moment. So I'm denoting it by m2. Okay, so therefore let me draw the figure once again, something like this. This is m1 vector and this is m2 vector. Okay, in the last part they are asking about to find out the magnitude of magnetic moment. Okay, so it is like I don't have to find the direction, but I have to proceed by considering the direction, because in the question they are not asking about the direction, they are asking only about the magnitude. So resultant magnitude, so since these are the vector quantities, so these has to be added according to the vectors addition. So therefore this is the figure, so this will become the resultant m. So this will become the resultant. If you draw the parallelogram, or if you draw the parallelogram around this, so this will going to give you the resultant parallelogram law of addition. This will going to give you the resultant magnetic moment. It will be m. So therefore the angle between two magnetic moment will be m1 and m2 will be 90. So therefore let's find out the magnetic moment. M vector magnitude is equals to m1 square plus m2 square plus 2m1 m2 cos theta, where theta is the angle between the two magnetic moment or the two vectors, and here theta is equals to 90 degree. So this will simply comes out to be m1 square plus m2 square. Okay, so therefore what do I know about this thing? It is given that the radius of the loop is r, so area will be pi r square. So therefore this will comes out to be m1 is equals to m2 is equals to, these are the magnitudes will comes out to be m1 is equals to m2 is equals to, let me write it as m net, this as m net and this as m. So m magnitude as I, that is the current which is given as I, into area, that is pi r square, I into pi r square. So therefore this will comes out to be m net, or the resultant magnetic moment magnitude will comes out to be under root m square plus m square, or else root 2m, or it will comes out to be root 2 I pi r square. So this will be the this will be the answer. Hence this is the answer. So this will be the magnetic magnitude of the magnetic moment, hence is the required answer. Now let's proceed towards the next example. If you look at the next example, find the magnitude of magnetic moment of the current carrying loop A, B, C, D, E, F, A. A, B, C, D, E, F, A. Okay. Each side of the loop is 10 centimeter long and the current in the loop is I is equals to 2 ampere. Okay, we have to find out the magnitude of the magnetic moment. Now we know that magnetic moment, we have to take the closed loop. So if we consider, if we look at the diagram, so it is like this: B, C, D, E, B, C, D, E. This is in the in which plane? Let me make the axis. This is Y, this is X, and this is Z. So this loop or this BCDE is in the YZ plane. The plane of this loop is in the YZ plane. So let me write over here that it is YZ. This is YZ plane, and this is in the, and this AB or BAFE, BAFE, this is in the plane, this is in the XY plane, XZ plane. This is in the XZ plane. So let me write it as XZ plane. Okay. So therefore, these are different. These two loops lie in the different plane, that is XZ or YZ. Now how to solve? Because what do we know? That if we want to find out the magnetic moment, we have to take the loop which lie only in the single plane. Now this is the complete loop which is lying in the both the plane. So it's easy to do this thing. Let's join this BE. So let's consider that according to this loop, join BE somewhat like this. So according to, let us assume that this BE, according to this, BE is carrying current for this ABEF. The current in the loop is this. So, and for the upper loop, it is CBDC. So for this, the current is in this. So if we, now we have taken two sides or the two wires, if we join these two wires, nothing will be left, everything will going to neutralize, because for this, for the lower one the current is going in this direction, and for the upper one the current is going in this direction. So this will going to neutralize because it is carrying opposite currents. So therefore this assumption is right, because nothing will going to come out from this if we superimpose these two. Now let's look at the magnetic moment. So magnetic moment of, let's take it this as the loop 1 and let's take this as the loop 2. Now what is the magnetic moment of 1? Magnetic moment of 1 will comes out to be, curl your fingers, this will comes out to be, this magnetic moment will comes out to be in which direction? It will comes out to be in the direction of minus x. Let me write it as minus x cap or minus I cap. So what will be the magnitude? Magnitude will be current into area. So what is the area? So we'll write this thing a little later. What is the current? So I'm leaving this as I into A, and this will be minus x cap. Okay. If we talk about, and this is the M1 vector, that is the magnetic moment due to because of the one loop. If we take this as a two loop, second loop, that is M2 vector will comes out to be I into area. Again I into area. Now what is the direction? Now guys, what is the direction of this thing? What is the direction of this? Now curl your fingers in the direction of current. Where it will going to point? It will going to point in the direction of minus y. Minus y cap or minus j cap. Have you noticed one thing, that if your loop is lying in the plane YZ, your magnetic moment, the direction of magnetic moment comes out to be in the direction, that is the third axis, minus x cap or x cap. This you have to check, like, but it comes out it comes out to be perpendicular to that loop. So therefore this will going to come out to be, M2 will going to come out to be minus y cap. Now if I make the diagram, this will look like as, this is M1 and this is M2. This is minus x cap m1, and this is minus y cap. So therefore the resultant will be this we have already started, that the resultant will be m net. So m net will comes out to be magnitude. Since in this question also they are asking about the magnitude, so m net will comes out to be under root m1 square plus m2 square. Here also the cos theta is 0 because theta is 90 degree. So therefore let me write it as what I'll get. So m1 will comes out to be I into area, and similarly this will also be the value of m2 also because the same current is going, areas are also same. So I, and this is equals to m. Let me write it as m. So I is given to as 2 amperes and the area. So okay, we have side is equals to 10 centimeter. So what we can write this as 0.1 meter. That means area will be a square. Area will be a square, or it will simply comes out to be 2 into 0.1 into 0.1. So this will comes out to be 0.02 ampere meter square. Okay. Now this is also m2. So therefore, if we look at this thing, m net will comes out to be root 2 m. So therefore, because this is m1 square plus m2 square under root, and these are same, these are m net is equals to this, and these are same, m1 and m2 are same. So therefore this will comes out to be root 2m. So therefore root 2 into 0.02 or 1.4 into 0.02, this will comes out to be nearly comes out to be 0.0028. This will comes out to be 0.028, yes, ampere meter square. And this is the required answer, m net, 0.0028 ampere meter square.
Hopefully guys you have understood the concepts and moreover the explanation for this part. So for the upcoming part, that is whatever we have done, like considering loop, whatever we have done in this part, the similar part we are going to do for the next part, but not with the loop but with a bar magnet. So for that upcoming part, stay tuned.